Today I want to tell you about some joint work with my collaborators Ben Grimmer from Hopkins and Kevin Shu, who's currently at Caltech, on Subgame perfect algorithms for smooth convex optimization. I'm sure that a lot of these keywords probably are new to some of you guys, so I'll try to go through everything relatively slowly. Here's the outline for the talk. I'll begin by telling you about the problem at hand. Right? The problem at hand is we want to design algorithms for smooth convex optimization. Right? Convex optimization today is not a tool, it's the problem. We want to design algorithms for performing smooth convex optimization. I'll give you a sort of a game theoretic view of this problem. This game theory will show up because it will give us language to talk about what it means for an algorithm to be doing well. Right, very loosely, right? This smooth convex optimization, this thing here, this is the problem that we care about solving. And an algorithm for solving this problem we will think of as a strategy for playing this game. Okay? And then right, this game theory will show up because it will allow us to say, what does it mean for an algorithm to be doing well? I'll tell you about this algorithm called the optimized gradient method, or OGM. This algorithm is due to Jordan Tabul as well as Kim and Fessler. This algorithm will turn out to be a maximin optimal strategy in the convex optimization game. Right? So in a very formal sense, it is an optimal algorithm. In a very formal sense, there is no algorithm that can outperform it. Then I'll tell you a little bit. I'll probably take a step back a little bit, and I'll talk about what it means for an algorithm to be maximin optimal. And I'll contrast that with a different notion of optimality called subgame perfect. Okay? It will turn out that subgame perfect is a stronger notion of optimality than maximin optimality. Right? So sort of intuitively, it will take into account sort of information that you've seen so far over the course of a game. All right? And then I'll tell you about this algorithm, the subgame perfect gradient method, that my collaborators and I developed that will turn out to be a subgame perfect strategy for the convex optimization game. Right, so again, in a very formal sense, it is an optimal algorithm, but now it is optimal for a criteria that is strictly stronger than what the previous algorithm was optimal for. OK. All right, so we'll start with this game theoretic view, or this game theoretic take, on smooth convex optimization. So our task today is we want to minimize some smooth convex function. Right? This is a problem at hand, and we want to design algorithms for minimizing this function. Right, this is a function that lives in Rd. A priori, the only thing that we know about our function, right? We don't know our function. We sort of need to. The only thing we know about our function a priori is that it is one smooth. Right? One smooth just means that its gradient does not change faster than sort of the gradient is a one Lipschitz function. We'll assume that f is convex, and we'll assume that f has a minimizer. Right? F has a minimizer just makes sense of this, makes sure that this is well-defined. Okay, we'll collect any function little f that satisfies these three constraints into this script f set. Right? Perhaps in CS lingo, I might call this script f right as my problem class, and this little f is an instance from my problem class. And the classic sort of way to formalize this setting, right, is that we will deal with a black box first order oracle setting. What this means is that our function, right, we don't have access to the function. We can't sort of look at the function ourselves. The only way we have access to the function is through an oracle. Right? There's an oracle that's provided to us that we can query. Okay, and this oracle provides the following sort of call. Right? We can query the oracle at a point x, and the oracle will return to us the function value at a point x, as well as the gradient of the function at the point x. Right? And instead of thinking about computational complexity, we'll be thinking about oracle complexity, right? The number of oracle calls that we need to make in order to approximately minimize this function. If we are in this black box first order oracle setting, right, then sort of any natural algorithm will follow this following template. Right, so this template is parameterized by some capital N. This is the budget. This is the number of times I'm allowed to query my first order oracle. And the algorithm will do the following. Right? So for each iteration indexed from 0 to capital N, what I'll do is I'll need to choose some query point. Right? Xn is my query point from the span of the previous GIs. GIs you should think of as being gradients, the gradients that we saw in previous iterations. And then we'll query our first order oracle for the function value and the gradient at that query point. Okay, so one thing to note here is that, for example, when n is equal to 0 in the 0th iteration, right, that set in the span will be empty, which is to say that x naught is necessarily the origin in RD. Okay, this makes sense because before we query any information about our function, right, every point in space is completely equivalent to every other point in space because sort of this function class, my problem class, is sort of affine translation invariant. Okay, and then in future iterates, right, what we'll need to do is we'll need to come up with a rule. Right, this is we need a rule for picking this query point xn in the span of these previous gradients. Okay, if you have a different rule, let's say a deterministic rule for now, if you pick a different rule, that will give you a different algorithm. Okay, and our question today is we want to understand what is the best rule for picking these query points xn in order to approximately minimize our function f. Okay, here you can see that there's sort of this tension going on between this step here and this step here. Right, we're trying to pick query points that will force the oracle to reveal to us useful information, whereas the oracle, in the worst case, could attempt to reveal very little information. Okay, so there's a very natural game theoretic way to think about this is the following game. All right, so we're going to consider this game played between Alice and Bob. The game is played over capital N rounds. N is fixed in advance. At the beginning, or sort of before the game starts, before the 0th round, Bob will secretly choose some function f from the problem class script f and fix an optimizer and optimal value of that function f. Okay. Then what happens is that over each round, Alice will be able to look at the history of all of these function values and gradient values that Bob reveals, and must pick then a xn in this span of these previous gradients. Right, this is the rule. These are the rules of the game. Right, Alice must pick some query point from this span, and then Bob will return the function value and the gradient at that query point. This game will proceed in this way for capital N iterations, and then at the end, Bob will pay Alice this ratio here. Okay, the reason that we set the ratio to be the payoff is that it means that, right, the reason that we set this is so that if Bob pays Alice $1,000, right, what that means is that Alice has successfully driven the suboptimality, right? This is the function value at the output minus the actual minimum value of the function, has driven the suboptimality down to 1/1000th of this normalization factor. Right, I won't go into why this is the right normalization factor, but you can imagine that without a normalization factor, it's impossible to do anything. Okay, so in this way, we have a bijection between good strategies for Alice in this convex minimization game. Right, if Alice can guarantee a large payoff that's completely equivalent, that's in one-to-one correspondence with a first-order method that guarantees a small normalized suboptimality. Okay. All right, something to notice here is that in terms of the information that Alice receives, right, over the course of this game, right, the fact that Bob fixes a function in advance, that's something that Alice somehow can never know. Right, for all intents and purposes, from Alice's point of view, right, Bob may not have fixed a function in advance. Right, Bob may just be playing scalar values fn and vector values gn, so that there exists some function matching. So there exists some instance matching these purported values. Okay, to make this more formal, right, that first version of the game is completely equivalent to the second version of the game. Right, so this is the version of the game that we will use for the remainder of the talk. Is that, again, the game proceeds in n rounds. Now, Bob no longer needs to fix in advance some function. Rather, Bob simply reports some scalar value fn and some vector value gn in every iteration. But what Bob does need to do is at the end of the game, Bob needs to convince Alice that he was not cheating, that there exists some function from our problem class that matches all of these function and gradient values that were reported earlier on in the game. Yeah, question?
How is this different from Bob knowing Alice's algorithm in advance?
Yeah. Bob is completely allowed to know sort of what Alice is doing up to a given iteration. Right? Bob can condition. Right? Bob can say, I know what Alice has done in the first n iterations, and how am I going to report fn and gn now? It turns out that will also be completely equivalent to Bob knowing Alice's entire algorithm as well.
I'm thinking of a minimax, so it's like Bob already knows everything Alice would do, and
Yep.
picking the worst case for Alice,
Right.
right?
Yeah. Exactly. So we will be. This is a minimax. Yeah.
Okay.
Yep. Yep. OK, so let's look at some classic optimization algorithms, and we will interpret them as strategies for Alice. Right? So gradient descent is a very natural algorithm. It's a very classic algorithm that goes back to Cauchy. Right? In gradient descent, what we do is at every iteration, we just take the current iterate and we subtract off the current gradient, and we'll call that the next iterate. Okay, I use this notation here, right? Xn minus 1 plus, right? The plus just indicates a gradient descent step. Okay, it turns out that you can prove the following. So for all instances from this problem class, gradient descent will give you the following guarantee, is that the final suboptimality is bounded by 1 over 2 times n times this normalization factor. Right? In other words, if Alice plays this, adopts the gradient descent strategy, then she can guarantee a payoff of at least 2n. Okay? So this is not optimal. Right? There's another algorithm called the fast gradient method, which is significantly better. This is an algorithm due to Nesterov. It also goes by the name of accelerated gradient descent. In accelerated gradient descent, you take a gradient descent step, but you add some momentum term. Right? This is sort of like going in, if you're going in a particular direction, you'll just keep going in that direction by a little amount. It's not too important for today what that momentum term is. But what you can prove about fast gradient method is that the suboptimality at the end, suitably normalized, can be bounded by 4 over n squared. Okay, so again, we can interpret this as a strategy for Alice that guarantees a n squared payoff. Okay, and in optimization, right, we would call this an accelerated convergence rate. Right, it's anything order n squared we usually refer to as an accelerated convergence rate. Okay. OK, so it turns out that this still is not optimal, and that we can design optimal algorithms. OK, so this brings me to the optimized gradient method due to Joy Tabul and Kim and Fessler. But the presentation I'll be presenting today is most closely related to Taylor and Bach 2019. So the optimized gradient method is a method that is very similar to Nesterov's fast gradient method. Right, what you do in each iteration is you can imagine that OGM, optimized gradient method, is going to inductively maintain a triple, right? A triple x naught tau naught z1 up until xn tau n z n plus 1. Right, I'll explain to you what these mean. The initialization is written here, right? So x naught tau naught z1 is equal to something. What it is specifically doesn't matter. What matters is what these iterates, right, what this triple satisfies. Right? We're going to try to prove something about these iterates inductively. So we're going to prove something is true at the base case, and then we're going to prove that, again, that property gets maintained through OGM's update rules. Okay, so the optimized gradient method, its initialization satisfies this following inductive hypothesis. Right, so this is really quite important, I think. Right, this is sort of what drives the optimized gradient method, and is also going to be what drives our algorithm later on down the road. Okay, so this is the inductive hypothesis that holds at x naught tau naught z1. What is it doing? Right, so here, right, this quantity here, right, what are we doing? Right, we're taking a single gradient descent step starting at x, and we're asking what is the suboptimality at that point. Right, this is going to be some non-negative quantity. Similarly, this point here is, this quantity here is asking how far is my z iterate from my optimal solution. That's also going to be some non-negative quantity. Right, we're bounding the sum of two non-negative quantities by something. Right, so what we can do is we can cover up one of these terms, and then we will still have a valid inequality. Right, this is still true, right, because I've just dropped a non-negative term. And it turns out that this quantity here, right, this inequality is actually still going to be a tight inequality. Right, in the worst case, there is a function f for which this inequality holds at equality, right, for which the suboptimality at this point is exactly equal to this upper bound. Right, so in that sense, we can think of that function as being a worst case function for this inequality. What happens, though, is that if that is the case, right, if this holds at equality, then it must be the case that this thing that I just dropped is equal to 0, which is to say that, right, this z is exactly equal to the minimizer. Right, so what we can take out of this is that if we have a function for which the suboptimality at x plus is large, then it must be that z is close to the optimizer. Similarly, we can repeat this exercise. Right, I can cover up this term now. It turns out that this is still a tight inequality in the sense that there are functions for which this z iterate is as far away from x star as x naught is from x star. Okay, but what happens is that if that is the case, then it must be true that x plus, by simply taking a single gradient descent step from x, I end up at an optimizer of my function. All right, so there's a smooth trade-off between the quality of x plus and z. Right, so this is what this inductive hypothesis is telling us. Okay. All right. So what OGM will do is, this is what is being proved under the hood, is that if you have a triple satisfying this inductive hypothesis, then there is a expressions that you can write down for how to update x hat, tau hat, z hat, so that the new triple x hat, tau hat, z hat also satisfies the inductive hypothesis. Right. The important thing here, intuitively, it makes sense that x hat we're going to choose to be some convex combination of x plus and z. Right. This is these are the two quantities that might be good in each of the worst case scenarios, but we don't know which scenario we're in. What's also interesting is that this tau hat, it's increasing at a rate of root tau. This is what gets you this accelerated convergence rate. Okay. If you do out this induction and you ask, what is the order of tau, it should be order n squared. Okay. Question?
I got lost. What is x plus again?
X plus is the result of taking a gradient descent step. Right? X plus is just regular gradient descent, and then doing anything else is doing something slightly fancier than gradient descent.
Yes.
Yep. Yeah, question?
Is the convex combination is going to be fixed regardless of what?
This is going to be something, the parameters here is a closed form expression in terms of tau. Right, tau sort of parameterizes this trade-off, and it also parameterizes how you should sort of trade off between these two worst case behaviors. Okay. All right. So this brings us to just the full presentation of the optimized gradient method. Right, we initialize so that this inductive hypothesis holds, and then we apply some update rule to maintain this inductive hypothesis. At the end, you'll get basically this equation here with capital N's replacing the ends, and then you'll just say that this term is non-zero, is non-negative, and you'll end up with the statement, that your suboptimality is bounded by 1 over tau n approximately from the initial distance squared. Okay, so this is the
Isn't your suboptimality after one more gradient?
Yeah, so that's why there's a slight modification for iteration n.
Oh,
Okay, so you just need to get rid of that plus, and then everything's good. So here are the guarantees of the optimized gradient method. So in 2016, Kim and Fessler proved that this tau n is exactly a lower bound on Alice's guaranteed payoff. We can guarantee that the suboptimality is bounded by 1 over twice tau n times the normalization factor. If this were the end of the story, if this were just a factor of 2 better than So for context, this is a factor of 2 better than the payoff you would get from Nestrov's fast gradient method. Okay. So this, the fact that it's a factor of 2 is not so interesting. What's more interesting is the fact that this is optimal. Assuming that you're working in large dimensions, you can imagine that you're working in really large dimensions and your iteration count is smaller than your dimension, then in fact there's no strategy that can guarantee a strictly larger payoff. Okay? So in other words, OGM is a solution to this variational problem where we are trying to maximize Alice's payoff over Alice's strategy, subject to Bob playing adversarially. Bob is trying to minimize Alice's payoff. Okay, so this is sort of the state of affairs in 2017, and at first glance the story is sort of over. There's not much better we can do. I'll come back to this in a little bit and sort of try to explain why I think that the story is not quite over. Okay, but I want to tell you first sort of the tools in this area and how people came up with these results. Okay, so these results were derived through this area of research called the Performance Estimation Program, or PEP, due to Jory Tabul in 2012 and Taylor et al. In 2017. The idea is that at a very high level, if there was a one-sentence description, is that PEP gives us a computer-assisted or computer-automated way to design and analyze algorithms. Okay, here is the idea in slightly more words. We can imagine fixing Alice's strategy. So we fixed Alice's strategy, so we know what Alice is going to do. And then we'll take that strategy and we'll give it to Bob. And then it turns out that if you fix Alice's strategy and you ask what is the worst case convergence rate of Alice's strategy, it turns out you can write this as a semi-definite program. Okay, there's a semi-definite program that will depend on Alice's strategy. Okay, but this is nice. Why? Because then I can sort of offload this to my computer. I can sort of try to discretize the search space of Alice's possible strategies, and then numerically look for the optimal algorithm. Only after finding the optimal algorithm do I then need to try to understand what it's doing or try to analyze it. Okay, so this is why there were a bunch of different names and different times for attributing the optimized gradient method, is because the optimized gradient method was found numerically for small n in 2012. And then sort of the algebraic formula for OGM for general n, as well as for small n as well, was only discovered a couple years later. Okay, obviously based off of the numerical result in 2012. And then again, sort of at the time in 2016, right, is a completely algebraic proof, right? We could algebraically prove that the algorithm was working, but we didn't really understand why it worked. And sort of the nice explanation that we know now sort of came later in 2019. Right, so there's sort of this sequence of steps in this area, right? In this area that I work on now in performance estimation, a lot of the results a lot of the timelines look like this, where we are able to numerically identify an algorithm much earlier than we can fully understand an algorithm. Okay, this story has been repeated in many different contexts by many different people, and is in different stages, right? So for some settings, we have numerically optimal algorithms. For some settings, we know algebraic formula for all the optimal algorithms. And in some settings, we sort of really understand intuitively what's going on. But you can see that this has been applied to a lot of settings, such as non-smooth convex optimization, composite optimization, distributed optimization, etc. Yeah?
So how, I would assume that solving the relevant SDPs is actually very painful and slow, but presumably not.
It's not bad. Yeah, I mean so I can give you a sense here. I sort of know the numbers here a little better. So you can go up to, right? So the size of this SDP. So the size will depend on the number of steps that you want to know, right? I want to know what is the optimal 10-step algorithm. I want to know what is the optimal 11-step algorithm. The size depends on n, and on a sort of small computer, you could, on my laptop, I'm able to solve these SDPs up to n equals 50, 100 maybe. But performing the non-convex solve, right, that is the algorithm design question, we can only do that up to maybe 25. But oftentimes, for a lot of these problems, you will start to notice patterns and be able to derive these algebraic closed form solutions from these solves up to 25 or so. Yeah. OK. Any other question? Yeah. Yeah.
Is this still an approximation, or are you getting the answer? It's just constrained where you can do so?
It's the exact answer, right? So the semi-definite program, this is a convex optimization problem I can feed to my computer, and there are a lot of off-the-shelf solvers that will let me find that solution. Yeah. OK. All right. One thing I want to mention here, though, is that in all of this literature, sort of the goal sort of has always been minimax optimal algorithms. That has sort of been our goalpost of where we're headed. And today, we're going to try to do something slightly different. Right? I sort of want to make the case that, hopefully, you'll believe me that minimax optimal algorithms is not, or maxi-min optimal algorithms is perhaps not the right goalpost. Right? Perhaps you want something stronger, and by stronger, I'm going to refer to this as the subgame perfect algorithms. OK, so what is the difference between minimax optimal and subgame perfect? Right, I'll try to make the distinction clear in a very simple game. Right? So we're going to consider a very simple game. Right? Forget about the convex optimization game momentarily. So there's a very simple game here between Bob and Alice. They're in line to grab pizza, right? And they are the last two, maybe they're in line at a lunch seminar, and they're the last two people in line to grab pizza, right? Bob is ahead of Alice in line, and when Bob gets to the table, right, there are 6 slices of pizza left. Okay. Since Bob is going first and there's one person behind him in line, Bob is allowed to take at most 3 slices of pizza in fairness to Alice. Right, so Bob chooses B is at most 3 and takes B slices of pizza. When Alice gets to the table, Alice is the last person. There's no one behind her, so she's allowed to take as much pizza as she wants of the remainder. Right? So A needs to be at most 6 minus B. Okay? We'll assume they're both hungry, so their payoff is exactly equal to the number of slices they get. So you probably, in your minds, have an idea of what the optimal strategy should be for Alice. But I'm going to ask you to consider this following strategy, where Alice commits to taking 3 slices of pizza sort of blindly, regardless of what Bob does. Right? Bob can do whatever. Alice will go up to the table and take 3 slices of pizza. What we can say about this algorithm is that Alice gets at least 3 slices of pizza in all scenarios. this is true. Regardless of what Bob does, Alice gets 3 slices of pizza. It's also true that there's no strategy for Alice that can guarantee strictly larger than 3 slices of pizza. Right? In the worst case, Bob takes 3 slices, and Alice is forced to take, at most, 3 slices of pizza. So again, this strategy is maximum and optimal, just the same situation that we were in the previous setting. All right, so hopefully this does not match with your notion of what the optimal strategy for Alice should be. Right? Hopefully, right, you agree that the optimal strategy for Alice should be to take the remainder of the pizza. All right, so what went wrong here? What went wrong is that we're playing a sequential game. Right? People take turns making decisions. Right? Decisions are not made all at the same time. Right, we're taking turns making decisions, and in a sequential game, I claim that we should demand a subgame perfect strategy, not just a maximum and optimal strategy. Okay, so just as some explanation, right? A subgame, you can think of that as the remainder of a game after some number of actions have been fixed, right? So for example, before any actions have been taken, that is a subgame. That's a valid subgame. But also, if Bob commits to taking 1 slice of pizza, that the remainder of the game then is also a subgame. Right? We can identify a subgame with a sequence of committed actions. Right? That's how I will sort of enumerate my subgames. So for example, in the seminar pizza line game, right, the empty set, that corresponds to the subgame of the pizza line game where no actions have been taken yet. Right? So that's just the original game. B is equal to 0. That's the subgame where Bob has taken 0 slices of pizza, and now it's Alice's turn to make a decision. And there are all these subgames, B is equal to 0 up to B is equal to 3. Now we will say a strategy for Alice is subgame perfect if in every subgame, right, no matter what subgame you're in, right, Alice's payoff in that subgame matches the best payoff she could get in that subgame, knowing that she's in the subgame. Okay, so for example, if we took this subgame here to be the empty set, right, the original game, right, the optimal payoff in the empty game, or in the original game, is 3 slices of pizza, right? So Alice must be able to guarantee 3 slices of pizza no matter what Bob does. But once Bob commits to an action, let's say B is equal to 0, right? Now, what is Alice's best payoff in this subgame is going to be 6 slices of pizza, right? So a subgame perfect algorithm is one that guarantees the best possible payoff in every subgame. Okay. And thankfully, this strategy, or this notion of optimality now matches what hopefully intuitively we agree to be the optimal strategy. The only subgame perfect strategy is for Alice to take the remainder of the pizza. Okay, now question?
In terms of like smooth convex optimization, what was the reason for like the initial like prioritization of like the maximum algorithm? Like why were people making this kind of like cynical assumption that whoever's providing that optimization problem is like acting in an adversarial way?
Yeah, so I mean, I think this goes back to like, we in the CS theory community too, people want worst case convergence guarantees oftentimes, right? Here we also want worst case convergence guarantees, but sort of you can think of this as a worst case convergence guarantee conditioned on information, right? So if I could, I can't say why this was done, this was before my time, but if I were to guess, right, why people didn't consider this question is because sort of we lacked the tools to even ask this question, right? There's sort of like trying to understand this is a very difficult problem, at first glance, right? It's, I think it was, sort of a very monumental achievement to even get, right, Nestrov's fast gradient method, which is up to constants optimal for the max, right, sort of in this worst case setting. Right, only because we have access to this tool now, right? All this computational power that allows us to try to like numerically find optimal solutions, were we able to find the maximum and optimal algorithm (OGM), and now also to sort of extend that and push that towards subgame perfect algorithms. Yeah. Okay. All right. So hopefully now you believe me that subgame perfect and maximum and optimal, these are distinct notions. The next question is, does this matter for convex optimization? Right? Do I care about trying to find subgame perfect algorithms in the setting of smooth convex optimization? I think yes. Right? First off, it's a very natural notion in a sequential game, which we are playing. But more importantly, right, oftentimes in practice, we are not dealing with adversarial functions. Right? And the fact that our function is not adversarial, we can model that as saying that Bob has played the game suboptimally. Right, we can't sort of, posit that Bob is going to play the game suboptimally in the future, but we already have evidence. We already know that Bob has played the game suboptimally in the past, right? In my iterations 0 through n-1, say. And so Alice should capitalize on this behavior. And also, I'll show you numerical evidence in a little bit that shows that by designing algorithms that are subgame perfect, we actually get much stronger numerical performance compared to the optimized gradient method. OK. So finally, I'm going to tell you about the subgame perfect gradient method. OK, so here is the optimized gradient method just revisited once again. Right? So here, right, just as a reminder, we initialize in order to satisfy some inductive hypothesis. And then you can think of inserting this sort of trivial step here where I'll take x tilde, tau tilde, z tilde to just be any triple satisfying the inductive hypothesis. And then what I'm going to do is I'll apply OGM to this triple. OK, applying OGM's update to this triple. Right, so to recover OGM, what we would do is we would set x tilde, tau tilde, z tilde to be xn minus 1, tau n minus 1, and zn. OK, this is how we would recover OGM. But we could potentially find a better triple, right, based off of our history. Like after looking at our history, we might be able to find a triple that satisfies the inductive hypothesis, but with a larger value of tau. OK, so that's what we're going to do. Right, so at iteration n, we have observed the following history. Right, we know the first order information that we've received. These are all the oracle responses up until iteration n minus 1. So what we know about our function is that instead of just being an arbitrary function, we now know that the function, whatever it is, must satisfy all of these constraints. Right, it satisfies this first order information. So what we'll do is we'll write down, right, obviously you can write down this optimization problem, where we're going to try to maximize the value of tau tilde subject to the inductive hypothesis holding. Really, we want this inductive hypothesis to hold specifically for the f that we're handed. But we don't know what that f is, so we have to condition over all possible functions that might still be revealed. OK? So at first glance, this is going to be a very difficult problem to solve. Right? Obviously, you can write down the problem, but whether or not you can solve it is a different question. Thankfully, in this setting, there's sort of enough using the performance estimation tools. We can actually reformulate this and write this actually as a small, quote unquote small, convex optimization problem. Right? So in every step, right, what is the proposition? The proposition is that at every iteration of my convex optimization algorithm, I'm going to solve another convex optimization problem. Right? So I'm going to be using convex optimization to do my planning procedure for the remainder of this first order method. OK, I'll come back in a little bit to the computational requirements required for this. Here are, however, the guarantees of the subgame perfect gradient method. Is that now, right, Alice can guarantee, right, sorry, so imagine that we're in some intermediate iteration of our game, right? So we're in iteration little n, and we're asking, right, at iteration little n, what can we predict about the future, right? What is my guaranteed payoff at this point in time for the end of the game? Right, so conditioned on this information, Alice can guarantee a payoff of some function of our information h. I'll call that tau n of h. And we can prove this matching lower bound. Right? If we are in high dimensions again, then there's no strategy for Alice that can guarantee a strictly larger subgame payoff. Okay, so in words, right, this is just saying that SPGM is a subgame perfect algorithm. Okay. All right, so now let me get back to this computational overhead. Right, so in the nth iteration of the subgame perfect gradient method, I will need to solve that convex problem that I told you about. It turns out that this will be something akin to a non-negative least squares problem. It's not exactly, but it's very similar in spirit, in n variables. Right, so if we were to run an off-the-shelf solver, if we were to run, like, let's say, ellipsoid method or something like this, or an interior point method, we would get we would require order n times d storage in the nth iteration and order n times d plus n to the 3.5 time in iteration n. Okay, so this is a very large computational overhead. Right? Perhaps it should be surprising at first that this is even possible. Right? I could a subgame perfect algorithm most likely exists for any problem you could write down. The question is really, how expensive is it going to be to try to implement that problem? And it's perhaps surprising first off that it's some polynomial time implementable thing. However, if you actually want this to be practical, you probably want to bring these numbers down. So we also propose this following memory constrained version of SPGM, of subgame perfect gradient method, where you get to specify a user specified parameter k. k will sort of be up to a factor of 2 the number of vectors that you're going to store in your algorithm. And then what you'll do is you'll just replace sort of the set that we know our function lies in to sort of just be the last to just match the last k iterates of information. Right? This is not exactly this. We do something slightly more interesting than this in the paper, but at first glance it's sort of this. And then instead we'll solve this problem here. And again, you can reformulate this problem as now a genuinely small convex optimization problem. So then, right, the storage is going to be order k times d, and the computational cost per iteration is going to be kd plus k to the 3.5. Right? In experiments, we find that k, a constant like k is equal to 5, works very well. Right? So we don't need large values of k. And also just to, for reference, right, if you were to simply write down a gradient, if you were to simply look at a gradient, right, that would be order d time. Right, so this is of a similar, right, the same order if k is a constant. Yeah, question?
Can you say anything about how far you provably deviate from subgame perfectness?
No. Yeah.
Okay.
Oh, actually, okay. So we can say that if you fix a k in advance, right, then the algorithm that we design is still subgame perfect, but for a modified version of the game. The modified version of the game is a game. It's sort of contrived, but it's a game where Bob can cheat as much as he wants, as long as Alice cannot prove that he cheats by looking only at the last k iterations. Yeah. Yeah, question?
So I think this is related, but so what's the trade-off for only considering the last k vectors?
Yeah, so the trade-off is that in each iteration we can perform the required computations much faster. We lose sort of the nice theoretical guarantees. There's sort of this theoretical guarantee that I sort of just told you guys about. But numerically, we don't lose too much. Yeah. OK. All right. So in the last little bit, I'll tell you about the numerical results. OK. So we ran some experiments. So here are just a couple of the types of experiments. These are smooth convex functions. Right? The first class of smooth convex functions are these regularized regression problems. Right? So you can think of this as L1 norm regularized regression. And then we also saw some problems related to like regularized logistic regression problems. You can think of this as these log sum x functions. Okay, we used a combination of real data as well as simulated data. And here are the experiments. Right? So for in the top row, we have random instances, right? Instances using simulated data. On the bottom row, we have instances using real data. For each of these plots, right, maybe let's focus on this top left one for now. Right, what is this plot showing? Right, we have some number. We have a test bed of problems on simulated data. And the question we're asking is, after some number of iterations, how many of those instances, what fraction of those instances have we solved to 10 to the negative 3 accuracy? Okay, so we want an algorithm that shoots up really quickly and then hits 100% early. Okay, the best algorithm here is SPGM. SPGM is this new algorithm that we designed. It's in red. Right, it relatively quickly shoots up to after just 10 iterations, it solves about 80% of all of the instances in our test bed. Okay, to this 10 to the negative 3 accuracy. You can compare that to other algorithms, perhaps notably OGM. Right, this is the direct competitor. Right, this is the prior state of the art. OGM is this dark blue algorithm. You can see it lags behind. Right, it's this one down here. Okay, it takes a long time to close the gap. To 10 to the negative 3 to 10 to the negative 6 on a lot of our instances. Down here, we can see that there's another algorithm, the BFGS algorithm, this is an algorithm that works very well practically, but it has no non-asymptotic, or it has some non-asymptotic guarantees, but they all sort of depend on dimension, which is something that we want to get around. Right? They're dimension-dependent non-asymptotic guarantees. Okay. Here are some more experiments.
So I guess like you're performing well in terms of number of iterations.
Yes.
In terms of computational complexity, though, how much more painful is it to have to solve these convex programs?
Yeah. So we didn't do this in this paper. Ben, my collaborator, has a student who has written code and to really optimize our subproblem solver. And for that, I think even in wall clock time, it's very comparable to BFGS, which is sort of the best practical thing to do.
And BFGS is like second order.
No, it's not second order. It maintains a matrix,
Okay.
right? But
Oh,
it's
a quasi.
it's a quasi-Newton, yeah.
So,
Yeah, so it's still technically a first order method. It just has sort of more memory that it uses under the hood. Yep. Okay, here's a different graph, right? So we can imagine we're in some intermediate iteration. Let's say we're at iteration 10, and we're going to say at this point in the game, if Alice were to play optimally and Bob were also to play optimally, right? What is going to be the payoff at the end of the game, right? What is Alice's payoff at the end of the game, right? So right at iteration n, right? If Bob makes a mistake, right, and gives you more information than he should have, right, then the graph will shoot up. If Alice makes a mistake, if Alice does not capitalize on the information that Bob revealed, then it will go down, etc. Okay, so this picture here on the left is I think this was from a experiment with random simulated data, I believe. Okay. So here we can see that this red curve, it goes up and it goes up quite sharply. Right, there are a couple of iterations where Bob really makes a mistake. Right, Bob reveals way more information than he should have, in which case we can capitalize on that information and ensure a larger payoff. Okay. Whereas if you look at the blue line is sort of the payoff, the same sort of value computed for the OGM iterate, right, the optimized gradient method iterate. You can see that number never really beats its original worst case value, right? So sort of in this situation, right, Bob is not revealing too much information, but also Alice is blundering, right? Right, this graph goes back down. Okay. In this experiment, right, this was an experiment with some real data. Right, this is a sonar data set from libsvm. You can see that, right, Alice's payoff just blows up very, very quickly, right? Sort of more or less, Alice has found an optimizer after, let's say, 25 iterations. I think something that's quite interesting to note here is that for the OGM iterates, right, these you can see that this, right, there's this oscillation in this OGM graph. Right, what's happening is that Bob is revealing more information than he should, but also simultaneously Alice is not capitalizing on the information and is taking a lower payoff than she could get. Right, so sort of, if you're in chess terms, perhaps, right, both of these players are just constantly blundering back and forth. Okay. All right. Okay. So let me summarize in the last 5 minutes. What are sort of the contributions in this paper? I think there are really two main contributions in the paper, right? The first is a conceptual contribution, where sort of we are saying, right, we're saying that these subgame perfect algorithms, these are really the things that we should be looking for, and furthermore that the subgame perfect algorithms, right, they are sometimes, right, in some situations, at least in this one, you can actually implement them with reasonable computational overhead. Okay, this subgame perfect idea I think is very nice because it more or less, right, in a very formal sense, right, in models, it captures exactly the fact that our function is not adversarial, right? When we actually try to minimize convex functions, when we call our optimization packages on functions of interest, right, we usually are not dealing with worst case functions. There's upcoming and future work. We have a paper that will hopefully be hitting archive soon for doing subgame perfect convex non-smooth optimization, right? So in the non-smooth setting, what should you be doing, right? Often there's this, in convex optimization, there's often this big divide between non-smooth methods and smooth methods. But even there too, we can design algorithms that have reasonable computational overhead that achieve this subgame perfect guarantee. There are also some other subgame perfect methods that we're working on for other settings that are still in the works, and hopefully at some point I can tell you about them. But if you're interested in any of these papers, this is this first paper on the archive about the subgame perfect gradient method for smooth convex optimization that I told you about today. All right, I'll stop here and I'll thank you for listening.